Hi everyone. This lesson focuses on the second part of the notes from 2.4, 2.5, and example 3 I think is technically from 2.6, but the examples all kind of go together. So for this lesson, you should have already looked at the first page of the notes where you copied down some important definitions and made sure you had the pictures of these graphs kind of established. And so really what I'm looking at here is how to calculate rate of change. So we wrote the definition down for rate of change already, but I just want to remind you that rate of change is always found by doing y2 minus y1 over x2 minus x1. And if that looks familiar to you, it should. That's the calculation for slope. That's how we calculate slope with a linear equation. Slope is a rate of change. That's exactly what slope is meant to measure, is a rate of change. The thing with slope is that with a linear equation, the rate of change is always constant. And I think you're going to see that when we get down to example 2. You'll see what I mean there. The rate of change always stays the same, and that's why it gets a fancy name. It's slope. But with other graphs, the rate of change depends on which two coordinates you're looking at. But it is helpful to be able to analyze that rate of change. And this is actually a concept that's going to be really big when you get to calculus eventually too. So, okay, so looking at this first one, to find the rate of change between x equals 1 and x equals 2, or really anywhere, the first thing we need is coordinates. We have x's for our coordinates, but we don't have y's. So I need to turn each one of these into like an xy coordinate by plugging 1 into the equation here. So I'm doing negative 3 times 1 squared, and actually I think I'm going to write it up above just to not use up all my space. So if I put 1 in here, negative 3 times 1 gives me negative 3. So this is the coordinate 1, negative 3. If I plug a 2 in here, 2 squared is 4, negative 3 times 4 is negative 12. So this is the coordinate 2, negative 12. And then I'm going to apply the rate of change formula. So I'm going to do y2 minus y1, so negative 12 minus negative 3 over 2 minus 1. So this really becomes a plus, so I end up with negative 9 over 1, which is just negative 9. So between those 2 points, if I were to look at this graph between x equals 1 and x equals 2, that means the y values are dropping by 9 for every step along the x-axis you take. Now let's do the same thing between x equals 2 and x equals 5. Again, I'm going to start with coordinates. Now for x equals 2, I already know the coordinate. The coordinate is 2 comma negative 12. For x equals 5, 5 squared is 25, and then times negative 3, so this would be 5 and then negative 75. So a rate of change would be negative 75 minus negative 12 over 5 minus 2. Change in y's versus change in x's. So negative 75 plus 12 is really what that works out to be. So that should be negative 63 divided by 5 minus 2 is 3, and then that works out to be negative 21 for your rate of change. I should point out, a lot of the times rate of change comes out as a fraction, kind of a fluke that I gave you two here that came out as whole numbers. Don't be freaked out if it comes out as a fraction. That's okay, it's a ratio. Okay, it's a rate. And so this negative 21 is saying that if I were to look in general between x equals 2 and x equals 5, our y values are dropping about 21 places for every step along the x-axis you take, okay, on average. So now let's look at the function just 5x. All right, so we're going to start the same way. We're going to make these coordinates. So when I plug in 1, 5 times 1 is just 5, so we end up with 1 comma 5. 5 times 2 is 10, so we end up with 2 comma 10. And so rate of change would be 10 minus 5 over 2 minus 1. That's going to be 5 over 1, which is really just 5. Okay, so there's my rate of change for that one. Let's look at the next one, x equals 2 and x equals 5. So my x equals 2, again, is 2 comma 10. If I plug in a 5, 5 times 5 is 25. So I end up with 25 minus 10 over 5 minus 2. That's 15 over 3, which works out to be also 5. Okay? So the special thing about this function is that because this function is linear, the rate of change is constant. It always stays the same. It wouldn't matter which x values I give you. It wouldn't matter what pair of x values I gave you. Your rate of change is always going to come out to be 5. And that happens to be this number right here. That's the slope. That constant rate of change is your slope. And that slope in direct variation situations is your k value. Okay? Notice that didn't happen up here because you had a square in the equation. But if anytime you're working with a linear equation, you should be able to tell me the rate of change just by looking at the equation. So that should actually save you some time. You shouldn't have to go through that with that calculation. But if you forget or you just don't want to rely on knowing that, you can do this process every time, and that's fine. Okay. One more. Let's look at one that has to do with inverse variation. And if you're watching this before you do lesson 2.6, that's okay. But just know that this same process applies with inverse variation. So just like before, I'm going to plug in my x equals 1. That's 12 divided by 1, so that'd be 12. I'm going to plug in my x equals 2, so 12 divided by 2 is 6. And I'm going to do rate of change. So 6 minus 12 over 2 minus 1 leaves me with negative 6 over 1, so I get a rate of change of negative 6. Okay, again, totally acceptable for a rate of change. So now when I look at 4 and 8, when I plug in a 4, 12 divided by 4 gives me 3. Whoops, sorry, not 12. My x value should have been 4 here. So I plugged in a 4 and I got 3 out as an answer. I plugged in an 8, and let's see, 12 over 8 is going to be 3 over 2, so that would be 1.5. So 1.5 minus 3 over 8 minus 4 gives me a negative 1.5 over 4. And I don't know what that comes out to be. Decimals or fractions are okay here. So I got negative 0.375. Which as a fraction would be 3/8. And I would take either one of those. So that's really what you need to know about rate of change, is that you're always finding how did the y's change versus how did the x's change, and then setting it up like a ratio and dividing. And that division is really what tells you the rate that the two things are changing at. Okay, that should be it for this section. Good luck with your homework.